Eaton's B-Line Series Quick Rail System is designed to help you save time, reduce complexity, and maximize the return on your investment. The Quick Rail system is completely field modifiable and easily accommodates future expansion. Quick Rail features a patented I-beam side rail splice retention groove to guide the splice in place and secures with only 2 bolts. Plus, the Quick Rail straight sections are available in both welded and bolted rung options. Installers no longer need to cut rungs in the field. Simply add a rung onto the bolted tray for additional cable support or to drop cables at a precise location. To speed up the process, we offer an Add a Rung kit that has everything you need to add a rung quickly and easily. The Quick Rail system has perforations along the side rail, which allows the attachment of accessories without having to drill holes. We offer multiple accessories to help ensure the proper bend radius of cables exiting the tray. These include the side rail dropout and the traditional rung dropout. We also offer accessories that provide cable pathway flexibility with outboard rungs that help separate or add cables outside of the tray in the future. If conduit is run along with the tray, we offer 2 conduit-to-tray attachments. For a quicker trapeze assembly, we offer the tab and lock solutions, which eliminate the need for hold-down clamps. By simply using a flathead screwdriver, the installer can position and lock the trapeze onto the threaded rod and then clamp the cable tray to the support assembly. The Quick Rail cable tray system is ideal for any project requiring a 12A or 12B load class. The system includes a wide range of straight sections, fittings, accessories, and covers. It is UL classified as a grounding conductor and is CSA certified. This makes the system ideal for cable management applications in commercial buildings, hospital and healthcare facilities, universities, data centers, and more. To save time, reduce complexity, and maximize the return on your investment, consider the Quick Rail system on your next project.
Eaton's Beeline Series BB2 telescoping box mounting bracket and box mounting clip allow for prefabrication of electrical assemblies, helping reduce installation time. The bracket features increased rigidity and a unique flange end that can mount multiple box steps and installs with only 2 screws. The unique bracket flange ends can be easily bent by following the specially indicated bend marks for mounting 1.5 inch and 2 1/8 inch deep boxes. By simply cutting and bending the flange end of the bracket, installers can now mount multi-gang boxes, 5-inch square boxes, masonry boxes, as well as speaker and strobe boxes. Boxes are easily mounted anywhere along the bracket using a toolless mounting clip, so now installers no longer need access to the inside of the box to attach it to the bracket, allowing for prefabrication of box assemblies. The bracket also withstands rigorous drywall installation and stays securely affixed to the studs. The box mounting clip stays securely attached to the bracket, ensuring that the box will stay in place. To provide added support for pipes and conduits, installers can use the toolless clamp, which easily snaps into place. When using the clamp to support copper pipes, we offer an insulator to help provide protection from differing metals. For one of the most versatile and rigid brackets in the market today, consider Eaton's Beeline Series BB2 telescoping box mounting bracket and accessories for your next installation project. To learn more, visit www.eaton.com/BB2.
Hello, I'm Shomi Sen, Global Director of Digital Solutions for Eaton's Crouse-Hinds Beeline and Oil and Gas Group. Now, even though I'm standing in the Houston Experience Center, I'd like you to imagine that this is a refinery, and all of this equipment that you see is in a Class 1 Division 1 environment. Class 1 Division 1 means that explosive gases are present under normal operating conditions. This is the most hazardous of classified areas, and here any form of ignition, like an arc, a spark, or even extreme heat, could cause an explosion. Here on the rack, we have our Crouse-Hinds Series Smart EBMX, which is an explosion-proof motor starter. Imagine that this EBMX is running a pump motor that sends water to a cooling tower for the steam turbines. If this critical pump fails, it could stop oil production. This unplanned and unexpected downtime could cost the refinery tens of thousands of dollars per hour. That cannot happen, and Eaton can help make sure it doesn't. Inside this EBMX is Eaton's Power Defense Circuit Breaker and Power Expert C445 Overload Relay, along with a wireless gateway and an explosion-proof antenna to connect to Brightlayer Industrial. By digitally enabling the EBMX and connecting it to Brightlayer Industrial, we are able to track and communicate a wide variety of live performance data. All this information can be seen on the Brightlayer dashboard above. Customers can see device status, so when we turn the motor on, the status went from ready to running. You can also see current and voltage data, temperature inside the enclosure, and breaker health status. This is important to our customers because now they have real-time access to data. We will now simulate a phase loss fault in the motor. Phase loss is a great example of a fault that a customer would want to be aware of immediately. A phase loss can occur due to loose or improper wiring or a blown fuse upstream. Once a phase is lost on a 3-phase motor, the motor may continue running. Physically, the motor will appear to be functioning as normal, so the customer may not even be aware that there's a problem. But this could result in unwanted motor vibrations, excessive heating, reduced efficiency, and eventually lead to motor failure. Remember that if this motor fails, critical production comes to a grinding halt. With Brightlayer Industrial and our digitally enabled EBMX, this phase loss fault triggers an immediate alarm in the app, communicating that there is a problem that should be investigated. You can see the alert on the dashboard. This alert can also be texted or emailed to identified individuals. That is the power of Brightlayer. As a customer, I don't need to be in this hazardous area monitoring my equipment. I don't even need to be monitoring my dashboard. Brightlayer will send me a text or an email when something needs my attention. This allows the customer to schedule planned preventative maintenance. A technician can service the motor on a customer's preferred schedule before the motor fails unexpectedly. This also prevents personnel from having to acquire a hot work permit. As you can see, digital solutions like these provide real customer value. By monitoring critical applications and providing actionable data, they improve safety, enable preventative maintenance, and avoid costly downtime.
As the cost of structural steel keeps climbing, the impact of reducing the quantity of supports can impact your bottom line. By using Eaton's B-Line series cable ladder, you can reduce the structural steel supports required, which can completely offset the cost of the cable ladder system altogether. The B-Line series cable ladder system is engineered to eliminate structural steel supports and provide more flexibility around placement of the support locations, all while maintaining the structural integrity of the system. This is accomplished by incorporating a number of features, including I-beam side rails for increased strength, splice plates that enhance structural integrity and allow for proper thermal expansion, as well as fitting design and use of tangents to maximize strength at fitting locations. All of these features result in a superior cable ladder system that allows customers to minimize their total installed cost by significantly reducing the number of structural steel supports. To help explain how this works, let's take a closer look at some key installation methods, starting with cable ladder straight sections. Traditionally, the industry's minimal support span interval is 3 meters. However, through Eaton's engineered I-beam design, the B-Line series straight sections allow for the structural supports to be spaced up to 6 meters with steel cable ladder and up to 12 meters with aluminum cable ladder, reducing the number of required supports by up to 75%. In addition, Eaton has created recommendations for its B-Line series fittings that fully comply with and exceed NEMA VE2 support recommendations. Our systems feature industry-leading 75mm to 100mm tangents that are specifically engineered to help maximize strength and carrying capacity of the complete system. Depending on the fitting being utilized, the installer can save up to 75% on support costs. For horizontal bends, if a ladder support is placed within 600 millimeters of each splice point, a fitting support is not required. If a support is dedicated to the fitting, then the allowable range for a ladder support near the splices increases from 600 millimeters to 3 meters. For horizontal crosses and horizontal tees, supports for the fittings, normally 3 to 4, are not required if a support is placed within 600 millimeters of each splice point. Also, if supports are dedicated to the fitting, the B-Line series cable ladder system only requires 2 supports for the fitting, and the allowable range for ladder supports near the splices increases from 600 millimeters to 3 meters. For vertical bends, the B-Line series system requires the use of only 1 support per fitting, rather than the 2 recommended by NEMA. This single support can be placed at any point along the fitting. In a typical industrial cable ladder application, multiple runs are utilized which increase the support layout complexity. In this specific example, 3 runs of cable ladder make a 90-degree horizontal change in direction, requiring a minimum 7 support per NEMA VE2. Utilizing B-Line support recommendations, the number of supports can be reduced to 3, resulting in lower cost and lower installation complexity. Next, let's review how Eaton splice plates and engineered I-beam provide proper support and superior flexibility throughout the system. NEMA VE2 recommends to support the adjustable splice locations within 600 millimeters of each splice location. With Eaton's B-Line series vertical adjustable splice plates, managing elevation transitions are simplified by eliminating supports on the inclined section of cable ladder. The vertical adjustable splice plates are designed to maintain the maximum load classification of the series of cable ladder utilized across the unsupported spans. Depending on the series utilized, incline spans between vertical adjustable splices can range from 3 meters up to 6 meters. Lastly, Eaton's B-Line series patented heavy-duty expansion splice solution is designed to eliminate supports and allow for proper thermal expansion with the cable tray system. The performance of the heavy-duty expansion splice, available in both steel and aluminum versions, complies with and exceeds NEMA VE2 support recommendations by eliminating the need to install 2 additional supports at every expansion location. Integrated sight windows allow for proper gap setting during installation, helping reduce installation errors. By utilizing B-Line series completed cable ladder system, composed of straight sections, fittings, and enhanced splice plates, customers can significantly reduce the number of structural steel supports while maintaining the system's structural integrity and exceeding industry standards. To see additional details on all of the recommendations, calculate your own savings, or schedule a technical training session, please visit eaton.com/SSS.
Hello and welcome to Eaton's Power Systems Experience Center in Houston, Texas. In this video, we'll be discussing fundamentals of classifying hazardous locations and the associated risk within these areas. Hazardous locations, or HAZLOCs, refers to industrial applications that either process, use, or store flammable material, thereby potentially creating explosive atmospheres. To reduce the risk of fire or explosion, classified areas must be properly identified. This classification is for overall purpose of protecting operators and minimizing the risk of equipment loss. The public will perhaps commonly identify oil and gas refineries as hazardous locations. However, classified areas are diverse and include food manufacturing, water treatment plants, and pharmaceutical production, to name a few. In essence, hazardous locations have the potential for a fire or explosion due to the presence of 3 elements: a fuel, an oxidizer, and an ignition source. Combined, these elements form what is commonly referred to as the fire triangle. A fuel is any flammable substance that can ignite and continue to burn. The second component is an oxidizer. Often, ambient air, which is about 20% oxygen, will be enough of a reactant, and the last element needed to start a fire is an ignition source. Electricity is a prime source of ignition because of equipment, such as switches and motor starters, can produce arcs or sparks in a normal operation. Other hazards are devices that produce heat, such as luminaires and motors. Here, service temperatures may exceed the safe limits of many flammable atmospheres. Hazardous locations are classified based on 3 categories: classification or type of combustible fuel. Groups are nested within classifications, which are sorted based on combustion characteristics. And finally, divisions, which consider the presence of flammable fuels within the operating environment as normal or abnormal. The National Electrical Code 500 is one of the governing code models that defines the division system that we'll be discussing here. Let's begin with classification. Hazardous materials are categorized into 3 classes based on fuel type. Class 1 is designated for flammable gases or vapors, such as acetylene and hydrogen. The gases and vapors are then divided into groups A, B, C, and D based on combustion characteristics. This chart is an example of a gas or vapor for each group. Class 2 atmospheric hazard is reserved for combustible dust, which are grouped based on combustion characteristic. Group B is for metallics such as aluminum. Group F covers carbonaceous dust like coal or coke. Group G is organic elements, sugar and starch, for example. Class 3 covers locations where combustible fibers or flyings are present. Some examples include industries that work with textiles, paper, or cotton. And finally, divisions, which identify the presence of flammable fuels in the operating environment as normal or abnormal. Division 1 covers locations where the hazardous material can exist under normal operating conditions. Division 1 is also referred to as normally hazardous. In Division 2 atmospheres, flammable fuels will be present only during abnormal conditions. For example, equipment failure or improper installation can lead to an ignitable concentration being present that otherwise would not be. There are two additional topics we need to discuss: flammable limits and T ratings. Flammable limit refers to the concentration of fuel needed in the atmosphere in relation to the oxidizer to create a fire. This is also commonly referred to as the ignitable mixture. The upper level is known as the upper flammable limit, and any concentration above this limit is too rich to ignite. On the lower end, the minimum amount of vapor or gas that must be in the atmosphere is the lower flammable limit. Any fuel in the atmosphere below this limit will be too lean to burn or explode. While discussing the fire triangle, I mentioned that a possible hazard is the heat that electrical equipment produces. The risk is that the heat can raise the normal atmosphere temperature, contributing to the auto-ignition temperature. Each flammable element has an auto-ignition temperature, which is the lowest temperature at which it will spontaneously ignite, without the need for an arc or spark. For this reason, the NEC includes the T rating table, which identifies the maximum temperature that each electrical equipment can reach within the classified location. For example, the auto-ignition of temperature for acetylene is 305 degrees Celsius. Therefore, according to the T rating chart, equipment in the environment must be rated T2 through T6. Here in the Houston Power Systems Experience Center, we've replicated a HAZLOC application to assist in training and education. For this video, it also allows us to show design differences between classified locations. For example, this cast panel board is rated for Class 1 Division 1 and is what we call an explosion-proof enclosure. This enclosure, on the other hand, is rated for a Class 1 Division 2 area, which allows us to use a stainless steel enclosure with encapsulated breakers. Here to answer some commonly asked questions is our hazardous location specialist.
In the US, we use NEC Articles 500 to 516. Overall, internationally, we have the IEC 679 standards. Some equipment has NEC and IEC markings, so the equipment can be adopted better globally, depending on your region. In the Gulf of Mexico, we have some floating assets, like drill ships, that use IEC 679. The NEC 505 code we use in the US is a variant of the IEC 679. NEC 505 class and zone seems to be growing more popular than NEC class and division, certainly in the Gulf of Mexico. You can use Division 1 equipment in a Division 2 location, but the certification testing is more stringent. However, you can't use Div 2 equipment in a Div 1 location. Class 1 is for gas locations and Class 2 is for dust areas. However, some equipment has both Class 1 and Class 2 markings on. When designing a facility, there is a team that looks at risk, and the electrical member of the team plans their equipment not to be in the hazardous location. For example, if you install a floodlight in an unclassified location, it could shine into the division location. Using unlisted equipment can save an initial cost and maintenance, but sometimes using HAZLOC listed equipment is unavoidable. There are different physical ways to mitigate an explosion happening with the equipment, and they are exclusion of the flammable substance, like pressurized, sometimes called purging equipment. Prevention of component sparks or hot surfaces, like a non-incendive system. Explosion quenching, like XP, explosion proof. And energy limitation, like what we call intrinsically safe.
Our hope is that this video has proven informative as an introduction to hazardous location classifications. To that end, the Eaton Engineering Service Group also offers various HAZLOC training courses. If you want to learn more about hazardous location design or discuss your HAZLOC application, please contact us or your local Eaton Crouse-Hinds sales representative to schedule a visit to one of our Eaton Power Systems Experience Centers today.
Hey Tom, do you run into a lot of questions about the NEC code?
Well, Dan, Article 250, grounding and bonding, that's a big area where there's a lot of confusion, and you'll get a lot of debates even at the code panels amongst engineers and installers on all the different terms that we have to use and getting everything the same and everything right. It's a target-rich environment for questions.
Rick, how about for electricians? I mean, is it really pretty straightforward, or do they kind of know what they're doing?
We run into a lot of confusion about grounding and bonding as far as transformers, bonding XO, when to bond, where to bond, with the different starts and stops of service, earth ground, building steel, foundation grounds. There's a lot of confusion based on that.
I mean, I see it with power quality. It's like, if it's 3-wire, 4-wire transfer switches, all this kind of stuff, even coming down the pole, going into the resi room here, where do we ground it, where do we bond it? I mean, at the end of the day, if a power quality person says they don't understand a problem, a lot of times, or if they act like they understand the problem, but they really don't, they might say, oh, it's grounding related, and they kind of just move on. That's a problem for me.
It's very confusing as an electrician to take the theory and apply it into the actual applications. So the more hands-on you can get with it, the better we can all become as installers and engineers, and more problems will get solved ahead of time instead of after the fact.
There's a lot of theory there. Getting your hands on equipment in facilities that provide that ability in an electrically safe, controlled environment, that's the key. That's where the rubber meets the road, actually seeing the fittings, seeing the bonding, and all of the meeting the National Electrical Code and practical application of grounding and bonding. It can't be replaced.
I agree.
Why are we talking about this? Why do we worry about grounding and bonding? We're worried about, and we want to establish an effective ground fault path, and we also want to think about those touch potentials or step potentials for two different reasons. First, the effective ground fault current path, we're intentionally constructing a low impedance conductive path that's designed to carry the fault current from the point of where the ground fault occurs in the system back to the source. And the reason we do that is we want to make sure that we open the overcurrent protective devices, which could be equipped with ground fault protection of equipment or GFCI protection. We want to make sure that we open those and give enough current for those to detect that fault. Now, you want that impedance to be as low as possible because we want to drive the fault current as high as possible. We have to understand the basic principles of ground fault currents will flow anywhere they can get a chance to. We're not going to guarantee that only the fault currents will flow through the equipment grounding conductor. And that's why we can't make the mistake of thinking that this grounding and this bonding will prevent someone from the electrical hazards of shock. When we talk about those electrical hazards of shock, we want to reduce our touch potentials or our step potentials. We want to keep everything at the same potential and be like that bird on a wire. So we expand this concept. If you think about the concept of touch potentials or step potentials and keeping things at the same potential, you can think about this in regard to substations, where we establish that grounding grid underneath the substation, or around swimming pools where we're doing equipotential bonding. This will reduce the likelihood of voltage potentials, and we understand that a potential difference between two voltages is what's going to drive current. So if we can reduce or eliminate that potential difference, we can reduce the likelihood of shock, so we can reduce the likelihood of damage to electrical equipment.
With respect to grounding, transformers are often an area of concern and discussion regarding when, where, how, and why to ground the transformer. This is a simple single-phase example of a transformer like a 480 to 120 volt control power transformer. Considering the secondary windings, one of the two legs, typically X2, would be connected to ground. This would allow you to establish a reference to a known reference on the secondary of the transformer when this is required for safety, power quality, or by NEC requirements. X2 is also considered the neutral conductor for typical low voltage applications and would only be grounded at the transformer and at no other point downstream on the circuit fed from the transformer. For this situation, a simple wire connecting X2 to the incoming ground wire coming from the primary of the transformer would suffice for a control power transformer. This ground would also be bonded to the transformer case to ensure that the case and all metal parts remain at a constant potential for reference to the known ground conductor. I've seen many instances where this ground connection was not done to supposedly make it better for power quality reasons, but yet it almost always made it worse without the ground connection, and electrical equipment was damaged. Why do we only connect ground once? Well, if we incorrectly ground the neutral downstream of the first connection, here's the problem. Load current will return on both the neutral and the ground conductor, which is connected to all the metal parts in the system. For that reason, current will divide at the subsequent neutral to ground bond, and load current will flow in the ground. We absolutely don't want current to flow in the ground conductors unless there's a ground fault. Having a single neutral to ground connection ensures that this will be the case. In this next section, we will explain how this applies to larger three-phase transformers.
Let's start with the simple definitions that we find in the National Electrical Code, or the NEC. And we're going to focus on Article 100, where most of the definitions are spelled out for us. Terminology is really important when we're communicating around grounding and bonding. So these definitions are going to be important so we're all speaking the same language. And what we're going to do is we're going to start with the term ground. The National Electrical Code tells us that ground is the earth. I think it's the shortest definition in the National Electrical Code. We define ground as the earth. So anywhere where you use the word ground, you're thinking you're tying to or you're connecting to the earth. Because the earth does not come with terminals, we have to establish a connection to earth, and we do that through what we call the grounding electrode. So a grounding electrode is a conducting object used to make a direct electrical connection to the earth. This is typically your ground rod, very common solution with regard to your grounding electrode. It could be your grounding grid, it could be the U for ground, or inside of a building it could be the structural steel, the water pipe coming into your home. Those are all grounding electrodes. And you could have multiple grounding electrodes at any one installation. And what the National Electrical Code tells us is that we need to connect all of those grounding electrodes together, and we create what the NEC calls the grounding electrode system. The grounding electrode system is when we pull all of those grounding electrodes together. So every grounding electrode that we have on that site, whether it be the U for ground, the water pipe, or other means that are identified in the National Electrical Code, we have to pull all of those together as a system. And that we call the grounding electrode system. Now let's talk about the grounding electrode conductor. This is the conductor used to connect the system neutral conductor or grounded phase conductor or the equipment to the grounding electrode system. Grounded, when we use the term grounded, this is when we say we are connected to the earth or to some body that extends that earth connection. Ungrounded is just the opposite, right? It's not connected to ground or to a conductive body that extends that ground connection. All right, so now we're going to talk about the grounded conductor. Now, this is the system or circuit conductor that is intentionally connected to the earth at that one point. We usually refer to this as the neutral. And its ugly brother, the ungrounded conductor, a circuit conductor that is not intentionally connected to the earth. So this is usually your phase conductors. Your grounding conductor. I know we're saying a lot of terms here with grounded conductor, ungrounded conductor. Now we're going to talk the grounding conductor. That's a conductor that is used to connect the equipment or the grounded circuit of a wiring system to a grounding electrode or to the grounding electrode system. Now, bonding and jumpers. So we're going to get into an area where we're pulling things together now. We're talking about bonding, and what the National Electrical Code defines bonded as connected to establish electrical continuity and conductivity. This is a very important term as we work throughout the power distribution system. Bonding conductors, or what we call jumpers. These are your reliable conductors to ensure the required electrical conductivity between metal parts required to be electrically connected together. Your service equipment, so when we get into service equipment, this is where your utility is connecting into the power distribution system. And in this equipment is where we're going to find some very important bonding jumpers. One of those is the main bonding jumper. The connection between the grounded circuit conductor and the equipment grounding conductor, or the supply side bonding jumper, or both at the service. So this is your main bonding jumper, that point where we pull both of those conductors or those systems together. Now your supply side bonding jumper, this is the conductor that's installed on the supply side of the service or within the service equipment enclosures, or for a separately derived system that ensures the required electrical conductivity between the metal parts that are all required to be electrically connected. Now we're going to move over to transformers for grounding and bonding inside of transformers. When we move into a transformer, we're talking more like in a separately derived system. This is your electrical source or other than a service having no direct connections to circuit conductors of any other electrical source other than those established by grounding and bonding connections. That's your separately derived source. So let's talk about that transformer. If I have a very common transformer you'll have in a power distribution system is your delta Y grounded transformer. There is an isolation between the primary and the secondary. You're establishing a separately derived system on the secondary of that transformer. And if we look over at a generator, you'll typically see people drive a ground rod next to a generator. And they'll bond the enclosure of that generator with that ground rod. If they connect the neutral to that enclosure inside the generator, they're establishing a separately derived system. Now, why is that important to understand that action will create a separately derived system? Because it will drive what you do in the transfer switch. If you bond that neutral to ground in the generator and you establish a separately derived system, you're going to need to switch the neutral in the transfer switch. And that would mean that you would need a 4-pole transfer switch instead of a 3-pole transfer switch. And if you're bonded in the generator and you're not switching the neutral, you have two separate areas where that neutral conductor is being bonded and you could have circulating currents. You could cause GFCIs or ground fault protection of equipment not to work and function correctly. A simple fix, if you didn't buy the right transfer switch, 3-pole transfer switch, and you bonded that neutral in the generator, is to just lift the bond in the generator. Your generator instructions will tell you how to do that. Now, we've established what a separately derived system is. And we know that depending upon, especially in the case of a generator, depending upon how you bond things in the generator and you establish a separately derived system, that will drive the solutions that you purchase and install. A non-separately derived system, good examples of those are your downstream panel boards, or that generator that doesn't have an established neutral ground bond in there where you're using the 3-wire or a 3-pole transfer switch. Those are your non-separately derived system. You're keeping things separate. You're keeping your grounded conductor separate from your equipment grounding conductors in all of those locations. All right, so let's talk about the system bonding jumper. This is the connection between the grounded circuit and the supply side bonding jumper. So we have a grounded circuit conductor out there. We have a system ground where we're establishing our ground, and we're going to need to bond those two together, and that's what this is all about. Your equipment bonding jumpers, these are your connections between two or more portions of the equipment grounding conductors. We have to make sure that we bond everything together, and anytime we put jumpers in between your equipment grounding conductor and any of the steel that needs to be bonded, those are your bonding jumpers. Equipment grounding conductor. So we've used that term, let's define it. The equipment grounding conductor is the conductive path that is part of an effective ground fault current path and connects metal parts of the equipment to the system neutral or grounded phase conductor. And that's done back in one location. Think of this as that bare copper conductor that you carry out to all of those loads. Or if you open up any receptacle, you'll see that bare copper conductor that's in the receptacle outlet. That is your equipment grounding conductor. We want that to be a low impedance and we want that to carry fault current should a fault occur, a ground fault occur in the system. All right, so everything that we've talked about so far has been about grounding and bonding of components and electrical systems. We're establishing that connection at the service or at our separately derived system between the grounded conductor and our equipment, bonding and ground and earth. Now we're going to talk about system grounding, and we're going to hit solidly grounded systems versus resistance or impedance grounded systems. Solidly grounded, when we use that type of terminology or that type of a system, we have a solid connection to the earth at some point in the power distribution system. There's no resistor or impedance inserted in that connection point. Ungrounded systems are just that. There's no connection to ground or a conductive body that extends that ground connection. We're insulated from ground. Your impedance or resistive grounded systems. These are systems that are connected to the ground, to the earth, through an impedance. All right, last statement about grounding, objectionable currents. Now, we use this term objectionable currents in Article 250 of the National Electrical Code, but you know there's no definition in the NEC. And when there's no definition, you know what you do? You make it up. So this is my definition. Current flowing on the effective ground fault current path during a non-faulted condition. And I think to best understand this, let's just talk about an example that you are probably well aware of because it received a lot of attention over at least the last 2 cycles in the National Electrical Code. And these are those motion sensor switches, type switches, that you'll find in either residential homes or commercial buildings, where you walk into a room and it turns the light on. If you think about how we wired residential homes or any types of structures when we came down to a light switch, what did we do? We brought one set of conductors, and that was our hot conductor. And we brought an equipment grounding conductor as well. And we did not bring a neutral. When we had a standard light switch, that was perfectly fine because we're just breaking one conductor. But when you install a product like a motion sensor switch, which needs to have power, so you need a neutral conductor to provide the potential voltage to power up electronics. If I opened up a light switch and I don't have that neutral conductor there, I could get that power by taking hot to ground, the equipment grounding conductor, to power up that unit, and it will work. But it would put current over the equipment grounding conductor. And based upon the definition that we just created and just talked about, that would be current flowing on the equipment grounding conductor that's not because of a faulted condition. That would be what we call objectionable current. And that is not permitted by the National Electrical Code. So changes have occurred over the last few cycles, 1, to prohibit the use of those products, and 2, to require the pulling of a neutral at those switch locations. So in case you installed a technology that required to be powered up, you're not likely to grab that equipment grounding conductor to get that done. You will properly use the neutral grounded conductor to get that done. So hopefully that helps you understand what we mean by objectionable currents. And remember, all of these terms that we just talked about, it's critical that we use these terms correctly as we communicate to make sure that we all understand each other and we get things right. And hopefully this little review helped you. For a larger electrical system, we have to consider many other things to properly ground and bond this electrical system. We will give a few examples of components and systems to hopefully clarify any confusion that may arise. Let's talk about 2 important terms, service entrance and separately derived systems. Simply put, think of service entrance as the electrical equipment fed from the utility source. This may include a transformer, a service disconnect, or other protective devices. There are very specific rules in the National Electrical Code for service entrance equipment and grounding. Think of a separately derived system as a point downstream of the service entrance equipment where electrical isolation creates a new source. Usually, this is a new transformer connection or perhaps a generator. In either case, a new grounding and bonding scheme is required for this separately derived system. Here's an example of a separately derived system with delta Y 3-phase transformers. Here is the grounding electrode conductor, and the main bonding jumper. This establishes the grounded conductor that we talked about in the previous section. Let's show you how a residential service and a load center are typically grounded and bonded. A residential system is a solidly grounded system with 2 HOTs and a grounded neutral conductor, which is a single wire. This allows the utility to ground the transformer and you to ground your main load center without dividing the current going back to the source because there's only 1 wire. NEC section 250.20b tells us that all premises wiring systems shall be grounded when the voltage to ground on the ungrounded conductors doesn't exceed 150 volts. So now let's look at a commercial power distribution system. As you get outside the residential world, you have more options based upon the applications. For example, data centers and other systems that demand a higher service continuity may opt to use high resistance grounded systems as opposed to solidly grounded systems. Many commercial and light industrial systems will be solidly grounded. Let's show you how a pad mounted transformer might be grounded and bonded, and how the indoor switchboard might be grounded and bonded for a solidly grounded commercial power distribution system. Finally, for larger systems using unit substations and switchgear, here's how the grounding and bonding is done for those systems. For larger systems like the pad mounted transformer or the switchgear, if the utility owns the transformer, we would see the neutral to ground bonding jumper installed inside our switchboard or switchgear, and we would bring the grounding electrode conductor into that service equipment. That is why it is clearly marked as service entrance equipment or suitable for use as service entrance equipment because it has the capability to bond the neutral to conductors inside that equipment. The transformer is a very important piece of a power system puzzle because it establishes the voltage levels and that neutral point on the power distribution system. Depending upon the winding type, the transformer establishes the configuration that you will have to use. For example, the transformer connection may be a typical one like the delta Y, or maybe more unusual like a delta zigzag or a high leg delta. Well-established methods for grounding and bonding these transformers can be found in our consulting application guide. Now, everything that we have just discussed around power system grounding is separate from the bonding discussion that we had because regardless of the grounding method for the power distribution system, the equipment grounding doesn't change and bonding is still critical and required. The difference is that the grounded conductor and the grounding conductor must be insulated from each other outside of one point in the power distribution system where they're bonded. Any subpanel in a power system must not have a connection from the grounded conductor, which is typically the neutral, to ground. Remember too, this is only relevant if you have a grounded conductor because with a delta high resistance system or an ungrounded system, you're not going to have that grounded conductor.
Power quality considerations are important as you consider when, where, how, and why to ground your power system. The key is to focus on things that can be controlled and solved. The main power quality concerns that are usually the focus of grounding studies include lack of proper grounding. Beyond the safety concerns, equipment can and will fail with improper or inadequate grounding. In addition, surge protection will be ineffective if it doesn't have a proper path for high-frequency currents. Improper wire size or type and painted surfaces. For example, 60 Hz currents will generally penetrate painted surfaces during fault conditions, but oftentimes higher frequency currents may or may not be adequate to provide low impedance path for stray or unwanted currents from electronic components or induced currents from PWM inverters. In most cases, highly stranded and braided cable or bus bar with the shortest possible length is the most appropriate grounding method for high frequency currents, as it provides significant surface area for the skin effect phenomena of high frequency currents. Circulating currents, ground loops, isolated grounds, and single point grounding. This can be a slippery slope, and oftentimes it's problematic to force a system to have a single point grounding for quote-unquote sensitive equipment. I've seen plenty of situations where ground loops from AV equipment has caused electrical noise and must be eliminated, but there are well-proven methods for dealing with this situation. It's often thought that dirty power grounds should be kept separate from the sensitive equipment grounds, but this is not only dangerous, but risky from a power quality standpoint and potentially damaging to equipment, aside from the fact that it's an NEC violation. We gave an example of a situation where isolated grounds were a problem with a lightning strike and improper grounding in our power quality solutions video. Isolated grounds like you would find on a hospital plug are a different story and can certainly help from a PQ standpoint, but should be installed with care and as intended. The bottom line is that PQ problems related to grounding can be handled, but they should be dealt with like any other power quality problem. Identify the symptom, find the source of the problem, and determine the right solution. But if the problem seems unsolvable, don't just blame it on grounding.
For systems with transfer switches, if separately derived systems are to be joined via a transfer scheme, only one neutral to ground connection must exist. Let me show you how you can accomplish this with a typical power system. So let's just take a quick look at an example system where you would have a transfer switch, and obviously you have your utility and your service panel. Off of your service panel, you'll have your grounding electrode. Your grounding electrode conductor will come up to your neutral bar, and then you'll have a bonding strap between your neutral bar and your equipment grounding bar. You'll have a feeder come off of your panel board and feed the transfer switch. On the other side of that transfer switch, we have a generator. The generator will be connected directly to the transfer switch, obviously through some overcurrent protective devices, and then your transfer switch is going to supply loads. So this is a basic layout of a transfer switch with a generator in a system. Now, sometimes people will drive a ground rod and bond the generator hull or the structure to that ground rod, and that ground rod is supplemental. So it's not required by the National Electrical Code. It is a supplemental type of grounding. A purposeful connection between the neutral, that grounded conductor, and that ground rod system, the grounding system over there on that generator, may occur in the field, either on purpose or by mistake. The important thing to understand is when you make that connection, you've established a separately derived system. So when I have a neutral conductor bonded and grounded in two separately derived systems, remember I have it grounded and bonded in my service panel, I have it grounded and bonded in my generator, I need to make sure that I only have one place where that occurs, and to get that done, I need to switch the neutral in the transfer switch. So that means I would need to have, say for example, a 4-pole transfer switch. If I do that, I put a 4-pole transfer switch in, I switch the neutral, everything is fine. A separately derived system implies that you would have a grounding electrode system and you would bond the neutral, the grounded conductor, in the generator with that system. If you have a separately derived system, the implication is that the transfer switch must switch the neutral with a 4-pole transfer switch. But what if I accidentally bonded the neutral to the ground in the generator and I only have a 3-pole transfer switch? How do I fix it? Do I have to buy a 4-pole transfer switch? Sure, you could. Or you could simply unbond the neutral in the generator. But you must be extremely careful on how you operate a system like this, because the return current for the generator neutral will flow back through the other separately derived system or transformer. This is especially important for the electrical workers who will be servicing the equipment.
Every day, Eaton helps power the world. But today is gone in an instant. And countless tomorrows with ever-increasing power needs are rushing in. Customers are demanding greater energy efficiency, alternative energy options, enhanced system reliability, and increased safety. Eaton excels at anticipating and meeting those needs. In a world with ever more complex power demands, Eaton's innovative solutions drive results. Our global capabilities ensure that we, as a single supplier, provide the solutions to keep your business up and running every step of the way. Explore the beyond with Eaton. Follow the charge.
The Champac LED wall pack from Eaton Krause Heinz is your solution for bright, durable, energy-efficient lighting in hazardous industrial conditions. Available in 3,000, 5,000, or 7,000 lumen models, Champac provides up to 116 lumens per watt, over 50% more efficient than the best available HID lighting. A wider beam spread will illuminate more work area with less fixtures, decreasing energy costs even further. Environmentally friendly LED technology eliminates the end-of-life cycle disposal costs associated with all types of HID lighting, and Champac is not a throwaway fixture. They're built to last 60,000 hours, with easily accessible drivers that make service or replacement a snap. Ideal for retrofit or new construction, Champac lights feature many contractor-friendly features for a speedier and safer installation. The lightweight 14-pound design is easy to handle, and the compact size fits in places other lights won't. 2 keyhole mounting brackets provide for a simple, secure, and easy leveled installation. Once mounted, simply open the front cover to make all your connections without having to hold the weight of the fixture. Champac's rugged design provides long-lasting performance in the harshest of environments. Stainless steel hardware, silicone gaskets, and a corrosion-resistant powder-coated finish are standard features that add up to NEMA 4X certification in IP66 ingress protection. Rated for the most extreme temperatures and marine conditions, Champac will provide bright, clean lighting. Wherever in the world you are, trust Champac wall packs from Eaton Krause Heinz to stay brighter, safer, and provide a real bottom-line savings.
It takes time and skill to align conduits on a trapeze and clamp them down to create a professional appearance. Sometimes it takes longer to attach the conduits to the trapeze than to hang the trapeze itself. We have a solution. Eaton's B-Line Series Conduit Trapeze Support, or BCTS. The BCTS incorporates properly placed holes that correctly space conduit and pipe for a quicker installation. The pipe easily slides through the bracket. To comply with NEC 358, simply secure the ends of the runs within 3 feet of the termination. This innovative solution installs up to 50% faster than traditional strut trapeze and reduces parts by up to 75%. To learn more about how Eaton's conduit trapeze support can increase your productivity and lower material costs, visit eaton.com.